Hi, my name is Prahalid, and today I'll be walking you through Lab 4 from Physics 2211. This lab focuses on oscillatory motion, which we analyze the movement of a mass attached to a spring along a curved path. To do this, we use video analysis software called Tracker to collect position data in both horizontal and vertical directions. We then simulated the same motion using GlowScript, which is essentially Web VPython, to calculate the expected trajectory and track how the system's energy changed over time. The key goals here were to apply Newton's second law to model the motion and compare theoretical problems with real data, and also to use the energy transformations in the system and use the energy principle for it. As for the principles, let's quickly go over the core physics concepts used. So first, we have Newton's second law, which tells us that the acceleration of an object results from the net force acting on it and its mass. So we used F equals ma as our foundation. We updated the velocity of the mass using the net force in time, and we used average velocity to estimate the updated position. Then there's the energy principle, which states that any change in the system's energy is due to work done by external forces. And in our system, since gravitational and spring forces are conservative, we assume no work is done by the surroundings, which means that the system's total energy should stay constant. So I guess let's go about what we did in the experiment. We observed a mass that swings in a curved arc while attached to a spring. Our system included the mass of spring in the Earth. Importantly, we assume that no external forces are acting on the system, so the surroundings were effectively zero. And using the tracker, we recorded the path of the mass over time and tracked its motion through its series of timestamp positions. We then fed these into our simulation to compare how closely the real world motion matched up with theoretical predictions. So continued to build our simulation, we use the initial setup parameters. We use the mass started at coordinates negative 0.112, negative 0.3632 meters. We also use a time step of 0.095 seconds. And the object's mass was 0.402 kg, and the spring constant was 6.83 n over m. We also assumed that the tracking markers were always centered on the mass's center of gravity, and that helped us keep the comparison between simulation and real data as accurate as possible. So regarding the code, this section shows the computational work done in code. The purpose is to numerically calculate forces, update position velocity, and plot the energy values as you can see here. So from these calculations, we were able to generate expected trajectories for comparison and compared every consistency by plotting energy values over time. So here's where we compared the theoretical values, or I guess to continue, we were able to generate the expected trajectories for comparison and also confirm the energy consistency by plotting energy values over time. So here's where we compare the theoretical values from the simulation to the observed values from tracker. So overall, the match between the two was very strong, especially in the horizontal direction. There were some minor mismatches in the vertical position, which was likely due, I guess, to a tracking error or some real world effects that we didn't capture in the simulation. So as for our sources of error, we noticed that there were a few possible sources of error in this thing. So the first thing to note is that the tracking of the motion manually in Tracker can be pretty tricky. And this is especially if the video is motion blur or low quality. Secondly, if the air resistance isn't since air resistance isn't modeled in our simulation, we have to recognize that it did exert a small force on the mass, but we didn't account for this in our thing, which could cause some small error problems. And thirdly, our system isn't truly isolated in the real world, so there might have been external influences causing non-zero work by the surroundings. So what does this mean? The question is the energy principle satisfied? And I guess the other question too, and the answer is yes, it was. The total energy shown by the orange line in our plot was remaining constant over time. And that's exactly what we expect in a closed system where only conservative forces are at play. Energy was conserved and simply transferred between kinetic, gravitational, and spring potential forms, and it was never created or destroyed. So, regarding what this means for the second question, we were able to compare the timing of oscillations from the x and y directions. You can see what they are here. And this difference ended up being 0.19 seconds, which is a small difference, but it shows that depending on how you track the motion, you estimate of your estimate of the period could definitely vary slightly. Overall, though, the oscillation timing was consistent, which gave us confidence in both our model and measurements. Thank you.